Today on How It's Made. Pipe cleaners. They'll drive you clean round the bend. Put that in your pipe, but don't smoke it. Blue Stilton cheese. Yes, please. When bad mould turns good. Smart electric meters. They're smarter than you think. And they're electric, obviously. And telescopes, taking you to another universe. But first... The pipe cleaner was invented early in the 20th century. A wire core with tufts of yarn, it can be bent and twisted into any tight space, making it useful for cleaning a lot of things besides pipes. Its flexibility also offers a creative opportunity for those with an artistic bent. Today, many pipe cleaners never get dirty. Instead of cleaning pipes, kids bend them and shape them to create crafts. A core component of every pipe cleaner is, of course, the wire, made of malleable steel. There are 2 wires in every pipe cleaner. The wires will become intertwined with tufts of yarn, and it all happens on a machine like this. But first, here's a look at the 2 wires twisting together without the yarn. This wire core is the heart of the pipe cleaner. Without the tight twists, the yarn would just slide off. The spools of yarn unwind at the same time as the wire and head towards the machine. They'll use cotton yarn for pipe cleaners destined for actual pipe cleaning because it's absorbent. For the craft market, polyester fibres are more suitable. The colours are brighter. This orange yarn and the wire travel over tension discs to prevent slackening that would cause messy entanglements as the pipe cleaner materials all head towards the forming machine. The yarn and the wire are totally in sync as they feed into the machine. The pile yarn rapidly winds around the metal former to coil it. At this point, the diameter of the pipe cleaner is set by using metal formers of different sizes. A sharp rotating blade cuts the coil to produce a series of short tufts. They stop the process briefly to give us a look inside. At the same time, the wires run in grooves around rotating rollers, and those yarn tufts now become trapped between the 2 wires. Together, the wire and yarn tufts then travel over rollers into a device called a flyer. The flyer was invented for twisting yarn. Each time the flyer rotates, it inserts 1 turn into the pipe cleaner. Bobbins then wind up the pipe cleaner. It all happens so fast, it's a bit of a blur. At the next station, numerous bobbins of pipe cleaners unwind simultaneously. They travel between a series of rollers. The rollers straighten the pipe cleaners, eliminating the curl created when they were wound onto the bobbins. A clamp then locks the pipe cleaners in position, and a carriage pulls them forward. The carriage moves in measured increments, so a guillotine blade can cut the pipe cleaners to a precise length. In this case, it's 15 centimetres, a popular length for the craft market. The machine ejects the completed pipe cleaners and a worker packs them for retail. Each bag contains all the colours of the rainbow and some. For thicker, fluffier pipe cleaners, they use a slightly different machine. Bobbins of polyester yarn rotate in a carousel to wind the yarn around a former and coil them. A sharp rotating blade cuts it into tufts. A carrier wire is used here to keep the pile under tension, after which the 2 core wires trap the tufts just as before. Another clamp twists the core wires and tufts as it pulls them forward. This transforms them into 1 thick and fuzzy pipe cleaner, which is then cut to any length the client orders. Production now focuses on pipe cleaners for medical and engineering cleaning jobs. Heat guns melt the fibres at the ends to seal them, ensuring they won't shed lint or fibres during the cleaning of sensitive equipment. You can see the difference this makes in the pipe cleaner on the right. Pipe cleaners today are no longer just for pipes. They're used to clean all kinds of things, like bicycle gears or any gear at all. They can also be used for paint touch-ups, odd jobs in the garage, cleaning rifle barrels, wrapping electronics cables, and cleaning any long tube. But of course, it's not all work and no play. There's always arts and crafts time. That's when things take a creative twist and pipe cleaners become anything you want them to. So there you go, the simple bare necessities of the pipe cleaner. Stilton is a creamy and crumbly British blue cheese whose roots date back to the early 1700s. It tastes mellower and less salty than many other varieties of blue cheese. Always produced in an 8-kilogram cylinder format, it has veins of blue mould radiating from the centre outwards. The production of Stilton is strictly regulated. Only half a dozen dairies in the world, located in 3 specific English counties, are licensed to produce it, and only from locally produced pasteurised milk. It takes 78 litres of milk to make each 8-kilogram cylinder of Stilton. They begin by pouring milk into a vat. Next, they add starter culture, laboratory-grown natural organisms. Then, they mix a blue mould culture called Penicillium roqueforti with distilled water. After about 3 hours, they stir in rennet, enzymes which coagulate the milk fat. After 90 minutes, workers run a wire knife through the now gelatinous milk, separating the fat, called curds, from the liquid, called whey. Then overnight, they drain the whey out of the bottom of the vat. The next morning, the firm curds go through a mill, which breaks them up into a crumbly consistency. Workers weigh out portions of 11 kilograms, each of which will become an 8-kilogram cylinder of cheese. After adding salt, the company won't disclose just how much, 2 workers gently hand-mix the portion. 2 different mixing styles blending the ingredients more thoroughly than one. Then they funnel each portion into a cylindrical plastic cheese mould, called a hoop. The curds still contain whey, so workers stack the hoops for 5 days. Typically, cheeses are pressed to drain the whey, not Stilton. Here, gravity does the job. The cheese drains under its own weight. Workers flip the hoop once daily to drain through both the top and bottom. After 5 days, they remove the hoop. The cheese, now drier, stands on its own, while with a knife, they perform a critical procedure called rubbing up. They rub the entire surface with a flat blade, sealing all the holes, so the air can't penetrate and cause premature internal mould growth. Now the cheese goes onto a stillage, a type of trolley, and begins its journey through the climate-controlled bluing rooms, named for the colour of the internal mould growth which occurs there. Workers flip the cheese daily to prevent its cylindrical shape from distorting under its own weight. Within a week to 10 days, greyish-white, sometimes orange naturally occurring mould begins growing on the outside. And from that point on, this growth is constantly monitored. After about 5 weeks, they mount the cheese on a turntable of a piercing machine. With each press of a foot pedal, the turntable rotates slightly, and long stainless steel needles pierce the cheese. These tiny holes permit oxygen to enter and kickstart the blue mould culture which the dairy put in the milk earlier on. Before long, blue mould gradually grows from the centre of the cheese outwards. To monitor the extent of the blue mould growth, the dairy's cheese graders draw samples using a tool called a cheese iron. The iron reaches all the way to the core of the cylinder. When the sample shows that the bluing runs right through, the cheese is ready, more or less. the timing's actually a bit tricky. Stilton is a relatively young cheese, best eaten between 12 and 14 weeks. The dairy does its best to coordinate shipping so that the cheese is at its optimum quality when it reaches the customer. Therefore, it ships 8 or 9-week-old cheese to local stores and a 7-week-old cheese to international customers, so that the blue Stilton will be an ideal 8 or 9 weeks of age when it arrives at its destination. So there you have the king of cheeses. Truly majestic. Coming up, telescopes, giving us a look into the future. And smart electric meters, so smart they'll read the meter themselves. See you after the break. Smart meters are electricity meters that don't have to be read by a person. Instead, they wirelessly send the information directly to your supplier. Your bill then shows how much electricity you used and when, making it easier to control your energy use. Old technology meters require someone to regularly read your meter. Smart meters can report consumption in real time by wireless transmission. Inside the smart meter are 3 different electronic circuit boards, the brains of the unit. They're built on large blank fiberglass panels. One panel yields 6 or 7 identical circuit boards, depending on the meter model. In the first machine, for tracking purposes, a laser etches a serial number for each future circuit board. The next machine applies a stencil in the pattern of the components to be mounted on the board, then spreads solder in paste form across it. The board now has solder paste, shaped and positioned exactly to receive the upcoming components. The next machine's 2 lasers verify that the solder paste application is perfect. Depending on the size of a specific circuit board component, there can be anywhere from 5 to 20,000 of them stored on a tape reel. Workers mount the reel for each component on what's known as the pick and place machine. This computer-controlled high-speed device picks the required parts off each reel and then places them in their designated solder-pasted position on the board. Bulkier components are stored on a different size reel, which workers mount on another type of pick-and-place machine. It does the same operation as the previous one, only slower, due to the larger size components. The boards now travel through a soldering oven. The precision-controlled temperature, peaking at 242 degrees Celsius, melts, then cools the solder paste, fusing all the components to the board. Next, each board undergoes testing. This machine applies electricity to ensure each and every component meets specifications. When the board gets the all clear, it moves to the next machine, which cuts it into separate circuit boards. Meanwhile, robots assemble the meter's digital display. They take a plastic half-circle housing and install a liquid crystal display into its rectangular window. At the next station, a robot uses a vision system to attach a circuit board to the liquid crystal display. Assembling the meter body begins with a plastic base plate. The first station prints a serial number on the bottom. The next station then flips the base plate upright and installs the components of the remote disconnect switch. This switch enables the electricity company to switch power on and off from any location. A switch cover closes up the base. The protruding wire will connect to a circuit board. The next station installs 2 terminals through the switch cover. These function as part of the switch operation, as well as part of the meter's measurement of electricity consumed. Once those terminals are in, an automatic screwdriver secures the switch cover. Now, the first of 3 circuit boards. This one, the metrology board, measures energy consumption. The unit comes off the automated line and a worker completes the assembly. He attaches a connector to the digital display's circuit board, installs the display, then connects the switch wire to the display's board. The metrology board sends its measurements to the display circuit board, which interprets the data and sends it to a third circuit board, which transmits it by radio frequency to the utility. Once workers have fully assembled the housing, they install a metal tamper evidence seal. Every meter undergoes rigorous final testing. An automated station verifies the display using a vision system. It checks that the meter measures electricity accurately and successfully transmits and receives messages. So fiddling the meter is a thing of the past. The telescope was invented by a Dutch optician 4 centuries ago. Before that, it was believed that the Earth was the centre of the universe. The theory that it actually revolved around the sun was eventually discounted, and in the hands of Italian astronomer Galileo, the telescope brought reality into focus. Modern telescopes are light years ahead of those early versions, and through their eyepieces, the universe continues to unfold. A reflecting telescope bounces and concentrates light with mirrors. Production begins with the machining of cylindrical metal parts. These are baffles, and when screwed together, they'll block stray light, which would interfere with the telescope's operation. More tools transform a solid aluminium disc into a ring with spokes. This part, called the spider, is a framework for supporting the telescope's secondary mirror. After coating the metal parts with a protective oxide, they plunge them into a vat of black dye. The dye soaks into the oxidized pores and seals the surface of the parts. Next, this molded disc of thick, low-expansion glass will become the telescope's primary mirror. A diamond-edged tool rotates on a calculated tilt to make the glass slightly concaved. To improve the concave profile, a worker coats the glass with abrasive. He adds a weight to a precisely curved cast iron disc and spins it. The weighted iron disc bears down on the abrasive-coated glass to fine-tune its curvature. A worker then examines the finely ground surface for scratches, and using a calibrated gauge, he measures the radius of the disc to confirm that the concave profile is precisely what it needs to be. The glass now spins, while a cylindrical cutter aims dead center to cut out a hole. This center hole is sized to accommodate the baffles we saw earlier, and it will also enable the mirror to be held securely in the telescope. Next, the glass disc oscillates, as an automated tool rubs a compound against it to polish it. A worker then applies some of the compound onto a polishing disc and works the surface of the glass against it repeatedly. This hand polishing improves the surface considerably. In the lab, a technician compares the primary mirror glass to a grid to verify that the dimensions are accurate. He aims a laser at the glass. A computer analyzes the reflected light. If the angle is off by 1/1000th of a width of a human hair, the telescope's image could be blurry. The glass is now ready for its mirror finish. They lock it face down in a vacuum chamber. They add small amounts of titanium oxide, silicon monoxide, and aluminium. They close the chamber, tightly encasing the contents, and then pump out most of the air, creating a partial vacuum inside. They activate a 6,000-volt electrode. This sparks a glowing discharge of ions onto the now rotating glass disc. These ions blast any lingering contaminants from the glass to give it a serious cleaning. They heat the aluminium, titanium, and silicon pellets, which evaporate into a cloud of vapor. Atoms condense, landing on the surface of the glass to form a glossy mirror surface. It takes just minutes for this highly reflective coating to be applied. This telescope mirror is now ready to reflect light from the stars and planets in the sky. Next, a technician screws lenses into the metal housing for the primary mirror. He adds a mount mechanism for the eyepiece, complete with dials for focusing. He flips over the assembly and slides that precision-made mirror onto the housing. A cork ring cushions the mirror so a retaining ring can be installed without a scratch. The telescope's primary mirror is now secured to the housing. He pieces together the three-part baffle, then screws it to the lens holder, protruding from the centre of the telescope mirror. He joins the baffle and mirror assembly to the telescope tube. The tube has already been equipped with a secondary mirror, which will bounce reflected images from the primary mirror back for magnification and viewing. It's taken about 6 weeks to build this telescope, and now it's finally ready to help unravel the mysteries of the universe. So, we've driven you round the bend, showing you just what you can get up to with pipe cleaners. And indeed, how they turn the king of cheeses blue. And finally, smart meters, which know more about what's going on in your own home than you do.
And we're unravelling more hidden secrets behind everyday objects we take for granted this Tuesday night at 8 on Discovery in the brand new episode of How Do They Do It? Next, Auction Hunters.